Okay, cool. All right, well, welcome everyone to MLOpt. I'm not the host, but I'm introducing Daniel today. Daniel is a good friend of mine. He's a third-year PhD student in the CSC department at the University of California, San Diego, advised by Misha Belkin and Sanjoy Dasgupta. He earned his master's in computer science at Columbia, and he's currently a student researcher at Google Brain. He's supported by the ARCS Foundation Fellowship, and today he'll be talking to us about mechanism of feature learning in neural networks. Great, yeah, take it away.
Yeah, hi everyone. Thanks for the very generous introduction, Joe. So I'm very excited to and grateful to be invited and excited to tell you guys about what I've been working on. I work in deep learning theory kind of broadly, but I'm also interested, or I guess this is mainly through the lens of developing a practical deep learning theory. As soon as I have a theoretical result, I try to see like what are the kind of practical implications of what I'm trying to do. So in that kind of lens, like this talk very much fits into that, I think. I'm guessing not everyone maybe is familiar with like super familiar with like these kinds of terms. So I'll maybe go a little bit slower to like what I mean by like feature learning and those kinds of things. But to start, this is a talk about neural networks. It's not a surprise to anyone. I think that, neural networks have been doing or people have been using neural networks for pretty amazing things, particularly in language models. We have like human-like poem generation using neural networks. But there's a bunch of other applications of varying degrees of flash. I'll just move you guys into the corner. All over the place. So you have them in vision, self-driving cars, and these like text to image type models. Biology, neural networks are having a tremendous impact. And of course, in game playing, where this computer beat the best Go player in the world a few years ago. But despite this, or I guess all of this empirical success of neural networks is in spite of the fact that we don't have a predictive theory, and I may for how they work, and I may go so far as to say that we don't have a theory that explains basically any of these hyperparameter or optimizer choices. And I say how they affect generalization, but that's really just a formal way of saying like why do these different hyperparameter choices actually lead to improvement or a decrease in the performance of a neural network. And nobody really has a theory for it, so often you're forced to just tune over in an exhaustive manner all of these different hyperparameters that, and maybe use some of your intuition and experience from previous developments of these models to try to come up with an architecture. And so, for example, on the left here is like, a rather intimidating table of like a kind of brute force search you can do where for all of the different aspects of the neural network, you really just have to search over everything, like, your gradient descent batch size, your dropout rate for different parts of the network, maybe even for the optimizer, like various parameters of the optimizer, so on and so forth. Yep.
What's the transformation column there?
This thing? Oh, the transformation. Oh, I think this is just how they do the search. Don't focus too much on the slide, but it's just like, you search over these numbers and then the transformation is like how this search actually affects the thing you use. Wouldn't worry too much about this. Yeah, this is just like a visualization here. Okay, so there is, however, one notable exception to all of this mystery, which is that when you take a neural network to be infinitely wide, and I suppose in a particular scaling, but it's in a particular scaling, crucially, you recover a very predictable behavior, which is that the neural network trained by SGD or stochastic gradient descent returns a solution that is essentially equal to up to some minor details, kernel, what's called kernel regression. So in kernel regression is kind of like a very classical technique that's well understood. And it's a method of basically interpolating your data, drawing lines through your data to come up with some sort of reasonable solution. However, you in many cases lose something from this limit. So there are many settings where provably and empirically creating a finite width neural network will outperform its infinite width limit. So there's something missing in this picture. So this limit does not completely describe how neural networks work. And what is missing from this picture? And this is what I would think of as feature learning. If you wanted to define it formally, feature learning is, to me, truly this difference between a finite width neural network and an infinite width network. But intuitively, the kind of operating definition of feature learning is the process of extracting patterns and statistics from the data, specifically for some sort of downstream use to improve prediction quality. And by the way, if you have any questions, feel free to interrupt or comments. So what would be a specific example of such feature learning? I think is sort of the provable example of feature learning where you can get some provable benefits is the example of a multi-index model, or also known as a low-rank function. In this case, we'll look at polynomials. So in a general supervised learning setup, your goal is to learn some function f star that you don't know, but you assume exists and is the source of the labels of your data. And so in the case of low rank polynomials, this function is low rank because it only depends on a small number of coordinates. So in the case of I've written here, you maybe have your data is a 100-dimensional vector, but your target function is a polynomial that only depends on the first two coordinates. In particular, it's just the product of the first two coordinates. So it's this quadratic function. And for fixed kernels, they suffer from a very classic problem in machine learning, which is the curse of dimensionality. In particular, fixed kernels, such as the NTK, has no way of telling whether x1 is more important than x100 a priori, or x94 or whatever other coordinate. And so it tries to use all the coordinates equally. And the result of this is that a fixed kernel regression will perform pretty poorly on this problem of learning this low rank target function. And here we measure this through r squared. So this is the lower the r squared, the higher the error, basically. So the maximum, you want to get your r squared as close to 1 as possible. However, for this problem, our function only depends on the first two coordinates. And let's say you're some sort of a magician, and you can and you know that the function has this form beforehand. What you can do is you can throw out coordinates 3 through 100, and you reduce the dimension, the d parameter here, from 100 to 2. And if you actually use your fixed kernel regression on just the first two coordinates, you nail this problem. You get perfect performance. And theoretically, what this means is when you decrease d from 100 to 2, you need now only a constant number of samples to learn this function. This up there. So what's the takeaway? If you can learn these relevant features, which I'll say are these projections onto the first and second coordinates, and I'll write this as so E1 is like the first standard basis vector. So this is a projection onto this matrix is a truncated diagonal where you just have a 1 identity, where you just have a 1 in the top left corner and 0 everywhere else. So the features that you need to learn are, in words, just the first and second coordinate. So the kernel view of neural networks, probably that will be okay. The kernel view of neural networks is, and this is just what kernel regression does, is that you return some weighted combination of some inner product function. Here, this is just like an NTK function. and alpha is a set of coefficients. You do a linear combination of a similarity measure, basically, with points in your data set. But crucially, this inner product is using all coordinates equally. This just reduces your d equals 100 vector into a single scalar without ever modifying the dimensionality of your data. But we know this is incomplete because it doesn't capture feature learning. And so we can consider the following correction that takes into account potential feature learning that could happen, where instead of just looking at this inner product between 2 points and weighting all the dimensions equally, we consider an inner product in a particular space, which is defined by this M matrix. And I haven't said what this M matrix is yet, or like what kinds of properties even this M matrix would be desirable of this M matrix. But let's just say for now, this is going to be some learned M matrix. And I think there are two kind of ways of looking at this M matrix that we should keep in mind for the rest of the talk. One is that you're modifying an inner product, and the other is more in line with the feature learning perspective I've given in the previous slide, which is that equivalent to taking this inner product with the M sandwich between the X and Z, you can square root this M matrix, which we assume is positive definite or positive semi-definite, and you extract the features individually from the X and Z before you take the inner product. So what does this mean? Maybe we can give an example of this, of the equivalence of feature learning and modifying an inner product. So let's say we again have our low rank polynomial problem. And let's say we choose our M star, because we are this magician, to be this projection onto the first and second coordinates. And we'll represent this as the sum of these truncated diagonal identity matrices. And on the left, if we look at this inner product and we substitute in our M star, you reduce this inner product to just the inner product between the vectors with just the relevant features extracted. And what is this relevant feature extraction? Well, this is just M star to the 1/2 applied to each of these Z and X. And once again, we get this sample improvement from D squared to a constant number of samples. So what is this? How could such a mechanism of feature learning be implemented in neural networks? How should we think of neural networks as being able to do this kind of thing? And the way we can see this is by first considering a deep fully connected network, as in the case above, and just the input to the first layer of this network, and performing a singular value decomposition on W1. We extract these 3 different components, where U and V are the left and right singular values, or vectors, and S1 is just a matrix of singular values on the diagonal. So what happens is you apply W1 to X on the left side, and so S1 and V end up being applied to the data. And because U1 has orthonormal columns, this U1 is a unitary matrix that applies a rotation and a reflection on top of the transformation applied already by S1 and V1. And from this perspective, the learned features are these S1, V1 transpose X, which are equivalent under the previous description of neural network feature extraction through this M matrix, as applying the square root of W1 transpose W1 to X. And why is that the case? Well, because if you were to take this quantity W1 transpose W1 to the 1/2 X and use this 1/2 as some sort of learned M matrix, you get where this is your M, you get W1 transpose W1, which recovers these singular values and singular vectors, which we think of as the extracted features. Okay, so in this view, what we're seeing is that neural networks are actually doing feature learning or modifying the inner product through this particular transform M matrix, W1 transpose W1. And the first layer is not the only place where you have some sort of feature extraction happening. Feature extraction in neural networks is actually happening at every single layer, except at intermediate layers, features are no longer just extracted from the first layer embedding, but they're extracted from intermediate representations taken from these layers. So, for example, at layer sub L, you apply weight matrix WL, hence you're extracting features. I think there's an extra parentheses here, but WL transpose WL to the 1/2 from this X sub L. And you're doing this at every single layer. Okay, so we've kind of described how the feature learning system that we've introduced as an inner product modification can happen in neural networks, but we still have not addressed, okay, what is the actual nature of these features that are extracted? Like, what is the M star of a neural network? And if we look at functions, the neural network as simply a hierarchy of functions that are applied layer-wise to the intermediate representations of the network at each layer, what we actually find is that the features extracted from each of these inputs to each of these subnetworks are actually very highly structured. And this is what we formulate as the deep neural feature ansatz, which is that the features extracted or the M matrix learned at every step, at every layer of the neural network is proportional to a statistic called the average gradient outer product, which is taken with respect to the input of that particular layer. And this average gradient outer product, what is this? So you average over, here this indexes over all of your data that your neural network was trained on with some standard training procedure like SGD on MSE loss, let's say. And you take the gradient of your subnetwork with respect to that input. So this is different. This is in contrast to example for the derivative that you take when you look at the NTK, as that is the derivative with respect to the parameters. So really, this is a sensitivity of your function to the input XL. That's what a derivative is. It's a sensitivity. And here, this is effectively the average covariance of the sensitivity of your function with respect to the inputs at each layer. Okay, any questions so far? Okay.
So like, what do you mean when like a matrix is proportional to another matrix? Do you mean like that matrix is that get a constant scaling factor of the right hand side, or like the norms are proportional or something like that?
It's just the entries are constant scaling of each other. So these matrices are very close, up to a constant.
And like it's the same constant.
So this constant will be different for each layer. This constant will be different for each layer, and it will be different depending on the architecture and the data and so on and so forth.
Entries of the matrix for a given layer.
So for a given layer, it's the same constant for all the entries. So literally, this exactly means WL transpose WL equals this matrix times some constant.
Very cool.
Where that constant is allowed to change depending on anything you want, basically. But the point is the structure is the same.
Thanks. Daniel, question: which one's bigger? Is the W transpose W bigger, or I mean more like amplified, or is the one on the right more amplified? If you know what I mean.
I know what you mean. I think the right will be bigger. The AGOP will be bigger.
Cool.
Typically.
So like W transpose W is like an attenuated version of the one on the right, the AGOP.
Yeah, so I'm actually working this out now and like kind of future work. But I think, yeah, so if you actually look at the structure of this thing, you get a WL showing up, and then you get a bunch of other stuff. And I think this other stuff basically amplifies the WL that's there. Yeah.
And for a particular, just think of like an MLP, for example, as I go deeper in the layers, does the gap widen between the AGOP and the neural feature matrix, or does it get closer, or does it stay constant?
In terms of magnitudes or in terms of this correlation?
Correlation.
I think it basically stays pretty high throughout the network. I think there are some exceptions to that. like ResNet, it gets a little bit tricky. But I don't think there's a clear relationship between depth and the strength of this correlation for general architectures. I think you could even say depth can even improve depth. I think there are cases where depth improves it and depth worsens it. I'll say that.
Okay, interesting.
Yeah. Okay, so we've kicked the ball up the hill a little bit. So we still haven't said what this AGOP is. So this AGOP is the M star. But what is the AGOP? Why do we like this? So the AGOP, it's an average gradient out of product. And I described this as a statistic. And what it really is actually some sort of estimate of what I will call the expected gradient out of products, which has been studied a ton in sort of classical non-parametric statistics, especially for these low rank kinds of problems. And so let's dive into what this thing actually is. So at least motivated by the examples I told you guys about, the ideal M should extract the features that are relevant for the thing we're trying to predict. So in this low rank problem, well, I've written this gradient here, but why is this gradient useful? How should we think about why this gradient shows up? Well, what does it mean for an M matrix, or what does it mean, I should say, for a feature to be relevant? And here, let's just think about coordinates. What does it mean for a coordinate to be relevant? Well, for a coordinate to be relevant, it means that as you perturb that coordinate, the function you're estimating should also change. And this is what I've just said in words is actually a derivative. That's the definition of a derivative. So that's why the gradient shows up, because this is a vector that's saying, you know, how does my function depend on these different coordinates that show up? And we don't have access to the function f star because this is some hidden function that we assume to exist. But maybe we can try to estimate something on average. But we don't want to look at the average gradient because the average gradient can be 0, even if there is a lot of variation in the gradient. So instead, we do explicitly want to look at how does the gradient vary on average. And this variance is captured by this covariance matrix, which is here uncentered. You can center it if you'd like. It doesn't change a whole lot. It can help even. But nonetheless, you get this uncentered covariance matrix of the relevance of different coordinates to your target function f star. Notably, this EGOP, or expected gradient outer product, is a property, or a statistic, I should say, of the function you're estimating and the data distribution. So this depends not at all on the way you're trying to estimate this EGOP. So this is just as much of a hidden thing as the function f star itself. But what is nice about this EGOP is that, as desired, it does actually capture these relevant features. For this particular problem, your EGOP is this truncated identity matrix with just picking out these first 2 coordinates relevant for prediction. And if we recall back from our low rank problem, this was exactly the M star we wanted for extracting out these first 2 relevant coordinates to reduce our sample complexity. Well, this is all well and good, but you might say, hey, this is not a real data set. This is some sort of synthetic problem. Well, it turns out this is actually a decent model for a lot of problems that show up in real data sets. For example, there's this Street View house numbers data set where your goal is to identify the center digit in your image. Crucially, you're seeking out the center digit. So this is the digit that will always appear in some sort of small box, small region of the image. And that means that if you were to look at the target function, because you're looking for the center digit, the right digit and the left digit don't matter at all for your prediction. And not only do these digits, the left and right digits not matter, like whatever is in that part of the image doesn't matter. And furthermore, whatever's in the center of your image matters a lot. And if you were to estimate the AGOP of the target function for this problem, it's some sort of mask that just picks out the center of the image. And you can apply this mask directly, and you see that's what happens. And what is the analogous performance sample complexity improvement that you get? Well, if you were to use some sort of fixed kernel, like the Laplace kernel, you get like, say, 79% accuracy, and this performance jumps up to 86% accuracy with on the masked input when you transform all the data with the mask.
So you're using the AGOP together with a different kernel, right? It's sort of like it's like assisting some other kernel method, right? It's not being used by itself.
So yes, so the AGOP is your M matrix.
Yeah.
So if we remember how we introduced the M matrix, it's modifying the inner product in some other kernel.
Yeah, I see.
And here I'm using K. So here it's an inner product kernel, but it doesn't have to be an inner product kernel. Laplace kernel is like what's called the translation invariant kernel, but you're just replacing your K basically. And it still uses an inner product, just in a slightly different way. So you can still feel free to use an M matrix like this.
What happens if you get rid of K and just make the kernel Z transpose MX? Like just use M as your kernel, basically.
So if M is a matrix, this is just linear regression, I believe. Because this is, if K is an identity map, this is kernel regression with a linear kernel, which is equivalent to linear regression.
Yeah, so that's what I'm saying. Like if you took that M and made it the AGOP and just did linear kernel regression, do you see improvements too, or?
Well, it's like, I see what you're saying, actually. It's a good question. I mean, it's a little bit weird because you're already extracting some sort of linear feature that you think is relevant. But if assume you're in some sort of realizable case where the function you're trying to learn is linear, then learning this M matrix, learning the right linear feature to extract is the same as learning the line, which is the same as solving the regression problem anyway. So it's equally learning the M for linear regression, learning this M is as hard as learning the function. But okay, so this actually touches on a pretty important point. So learning the M is actually easier for unexplained theoretical reasons, is easier than learning the target function in a lot of cases. Or learning the M to some approximation, good enough approximation that it helps performance is easier than learning the target function. So for linear regression, learning the M is equally as hard because it's kind of by definition as linear regression. But for nonlinear problems, it's much easier usually, or important cases. Does that make sense?
Yeah, I think so. But so if you go back to the slide you were originally on, table. When you say AGOP, you mean the neural feature matrix, right?
I mean the AGOP. So there's an asterisk. So basically, right. So the function you're learning for SVHN, you can't just download this function. Like this is like real, organic data. But the way we estimate this expected gradient outer product is by taking a model that gets 97% accuracy and saying, okay, this model is so good that it's learned that it's basically equal to the target function. Actually, and so we get the AGOP of that model that's so good that's learned the target function that we just treated as the AGOP for this slide, at least.
Yeah, I see. Sorry, yeah, I was confused. I was trying to thought it was the feature matrix. But okay, keep going. Sorry.
Yeah, no problem. It's a confusing point. Yeah. Right. So this neural feature ansatz says you actually learn this thing. And so what does that imply? It implies that if you estimate this AGOP or EGOP using a method that has no feature learning, like a kernel method, you can actually recover the features of a neural network. So that's exactly what happens. So if you're predicting whether a celebrity face has some sort of characteristics, like if the person is wearing sunglasses or if the person is smiling, if you just estimate this AGOP from a kernel method for each of these tasks, you recover, here the top eigenvector, but it's actually the entire matrix that's extracted from a trained neural network now. Okay, so we now effectively have a closed form for the weights of a neural network, or at least the uncentered covariance of the weights. And let us not forget, what is the AGOP actually doing? It's measuring some sort of what are the relevant features for your task, and that's pretty well reflected by what these matrices actually look like. So for the task of glasses, the AGOP, the top eigenvector of the AGOP is like some mask that highlights the glasses. For smiling, it's this mask that kind of looks like a smiling face. So on, it's mustache, so on and so forth. And if you reinsert this learned M matrix back to the kernel method on a bunch of problems, but just on the problems we've discussed. So on SVHN and these low rank polynomials, you close this previously pretty large performance gap between deep networks and fixed kernels. Am I doing that time? Good. Yeah, so this is all well and good, but this is all for these kind of simple architectures, in particular, deep fully connected networks. But what about more realistic, more complicated architectures? And so the second half of the talk, I'll just talk about our results for CNNs. So there is an equivalent neural feature ansatz that you can define for convolutional neural networks. Here, now the weight matrices for convolutional neural networks are no longer acting on your entire input image at once. They're actually convolutional filters. So you have to define an analogous average gradient outer product that instead of averaging over the whole input image, it's averaging over patches in the input image, and then over all patches. And there's lots of weird things that people have noticed with convolutional neural networks. And one of these particularly cool things is that the filters of these neural networks recover edge detectors. And we find that the AGOP of kernel method will actually recover even cleaner edge detectors than the neural network. And when you apply these edge detectors as filters over images, they act as you might expect by looking at the actual matrix, and they extract features from relevant images, in particular in a way very similar to filters extracted from state-of-the-art architectures. So feature learning in convnets. So a little bit of preliminaries. So the notation gets a little bit more complicated than in fully connected networks, but effectively the structure of these networks is that they are hierarchically applied functions, just like fully connected networks, except now instead of multiplying the whole image by X, you convolve a filter WL at layer L over the input to layer L, X, which I'll call XL. And then you apply some function on top of that, which can include some sort of pooling operation and subsequent filter applications. And for convolutional nets, the input to the next layer at every layer is in fact an image on its own that is the result of passing all of the filters from the previous layer. And these images are of size at layer L, PL in width and height, let's say, and then QL in width. Or maybe I'll switch that. PL in width and then QL in height. And you can, as I've mentioned before, the kind of important substructure in these images when passed through convolutional neural networks is these patches, which are indicated by brackets. So patch ij is the patch centered at ij, is indicated by x bracket ij. And implicit in that is some sort of patch size, like let's say 3. So xij is the patch of size 3 centered at coordinate ij. And in order to describe this neural feature ansatz, we first have to unroll this convolution operation into a matrix multiplication, where the multiplication happens on each patch individually and independent, and we'll treat this as an independent multiplication for each of these different patches. And how many different patches are there, whether there's a patch centered at each of the possible X and Y coordinates of your image. Any questions on the setup? Okay. So what is the neural feature ansatz for convolutional networks? It states that the neural feature matrix for convnets, which is the uncentered covariance now of the filters, is again proportional to the average gradient outer product of the model with respect to each of these inputs, but then averaged over all of these independent inputs, or treated as independent inputs. In particular, you're averaging the gradient outer product over the data and over all of the patches in the image. And this again holds for all of the different layers. So now we can start to analyze real architectures here. So if you take the pre-trained models, if you go to Torch Vision, which is like PyTorch's vision library, has a bunch of these pre-trained models, including seminal models such as AlexNet, VGG, with and without batch norm, and various ResNets. And we see that the correlation, when we average across all the layers of these architectures between the average gradient outer product over patches and the convolutional NFMs, is consistently very high, so above 0.9. And this gets back to Joe's question. So in deeper ResNets, you can get some small decaying correlation, which may have to do with the fact that I think you get some sort of restriction of feature learning with really deep ResNets. But it's an interesting question. Something weird is happening in these deeper ResNets for sure. And this is reflected though qualitatively by a high correlation between the AGOPs and NFMs. Just visually between these, here we're just visualizing the correlation, I'll put it that way, between these different matrices. So this is for the state-of-the-art architectures, but we also tested, let's vary patch size, vary different pooling layers, and this correlation remains quite high across all of these different choices.
Daniel, that
Yep.
very like really deep networks, is it possible that that's because like you're averaging across filters as well? Like what if you just like retained the filters as they were, because like you're sort of calculating like what the quintessential filter does, right? Like you're looking at all the different filters, which all do different things. They all have individual AGOPs in some sense, and then you average over all of them, right?
Yeah, so we're averaging the correlation, not the matrices themselves. Yeah, that would be quite bad, I think. Like the correlation would be very bad. Yeah. Yeah. Definitely the filters will look, it's pretty interesting. So the filters in every layer will actually be edge detectors, and we'll see later, even at deeper layers. But they will be kind of, the deeper layers are very qualitatively different than, let's say, the first layer, right? Because channels in the first layer are color channels, but then colors in the later layers are channels from different filters that you've learned, right? So they're kind of apples to oranges.
I'm gonna ask you like in the beginning of the talk whether you were gonna talk about ResNets, because like that original claim that we made, which was that later layers act on the features created by the previous layers. With ResNets, you get like this additional boost where like you also pass the X again. So they don't necessarily have to if they don't want to.
Yeah, so it's a little bit, this is kind of this is a detailed discussion, but things get like a little bit weird with ResNets. The framework still works, but it's the way you have to treat things independently, basically. Like the intuition is like wherever the W gets applied, whenever you do some sort of matrix multiplication with W, that's the thing that's contributing to the ansatz. And that's the thing you should average over. And you should average over that thing in essentially treat it as some sort of independent input from wherever else that X gets used. But that's a detailed discussion. It's not super crucial to the message. Yeah. Okay, so for convolution, the visualizations are pretty revealing, I think. So we should definitely go into detail about what is the appropriate way to visualize these patch transformations. So for fully connected networks, I guess I'll go back actually. For fully connected networks, we visualize them, the features, by simply applying the matrix to the whole input. And this acted as a mask on this input image. But now in the convolutional case, we are applying a mask to each patch, because that is the acting recipient of the feature transformation. The features are extracted as in that description of m to the 1/2 applying to some vector being an extracted feature. Here the extracted feature is like m to the 1/2 times a patch. Okay, so what's the best way to visualize this? Well, if we want to understand like how are these patches modifying, how are these filters modifying images, we can once again apply, we want to apply the filter, or this m to the 1/2, to all of the patches in the image. So we patchify the image, we apply the filter to all the different patches. And then now we want to get, we have some, because we patchify the image, we now have like some much bigger image that contains all the different patches. And we now want to reduce this back to the size of an image again. So what we do is we just look at the norm of each of these patches as a representative for the whole patch. And what that means is, why does that make sense? Well, that's actually just reflecting like how much of that X component of that patch component was in the opposite of the kernel. So this would be like the what's the opposite of the matrix kernel? So it doesn't get mapped to 0, right? Of the m to the 1/2. And so intuitively, for example, like if m to the 1/2 is some sort of edge extractor from the patch, then this will have a large norm if the patch ij has a patch in it, as an edge in it. And if there's no edge in it, then this m to the 1/2 will, then this edgeless image will be in the kernel of this matrix. So this will have a small norm. And that's exactly what we see. So if we take these fully connected network, not fully connected networks, if we take these state-of-the-art models, VGG and Alex, or at least seminal and recently state-of-the-art models, VG11 and AlexNet, and we take a full resolution ImageNet image, and we perform exactly this visualization, we see that not only are the NFM and AGOP highly correlated with each other, but they're doing some sort of edge extraction. Even at intermediate layers, we see that you get even these more refined silhouettes of these objects. So this has been a description of the learning, but I think if you want to call something a mechanism, I think a really compelling way to do that is to introduce causal evidence that this AGOP is actually leading to some of the performance improvements that you get in neural networks over fixed kernels. And so that's exactly what we'll do, is we'll introduce the AGOP into fixed predictors, just as we did in those SVHN and low rank cases. Okay, so for two-dimensional inputs, so this is kind of an intro into convolutional kernels. These are not too much more complicated than regular fully connected kernels. Basically what they're doing is they apply a fully connected kernel that depends on some inner product, but now over all the patches in your input. And then it sums all of these pairwise kernels over all the patches. And in the same way we modified it for the fully connected network, we'll want to modify the inner product, except now on patches, by introducing this feature extracting M matrix. And we'll note that we'll vectorize these patches by flattening them over. So a patch is like some sort of 3x3 window, and then you also have to consider the different channels, which if there are like 3 colors, there's 3 color channels. So we'll just vectorize this. We'll flatten that whole thing into one C times Q squared vector if the patches are of width Q. And so this M matrix now is of size CQ squared by CQ squared. And we can now learn this M matrix by recursively learning this AGOP. And this is actually the same algorithm that we use in the fully connected case, except now we're learning this average AGOP over this average AGOP over patches, in addition to just averaging over the data. So here, where S is all of the two-dimensional patches that are utilized by the kernel predictor, the way this I guess, not a priori, I'll explain a little bit what this method is doing. So you you solve a regular kernel regression problem where you've done no feature learning, and that's what these first two steps are. So you compute some kernel matrix, and you solve it by inverting this matrix and applying that to the labels, and then you estimate the average gradient outer product of your kernel predictor, and you recursively substitute that back into to define some new kernel, which you again use to solve the predictor and get some new AGOP, and recursively do this procedure, so on and so forth, for maybe 5 iterations or something. And what we see is that this kind of procedure lets fixed kernels overcome proven limitations. This is supposed to be limitation, not imitation, of fixed kernels that CNNs don't have, a limitation that CNNs don't have. And this is local signal additivity. So this is, in this particular problem, what that means is that you have some sort of noisy background, but you have what we'll call a local signal, which is just, here it's some stripe that's either all ones or all -1s somewhere in your image. And when you apply the AGOP from the recursive kernel method, it dims out the noise to some extent and then highlights this band, regardless of the parity of the band. And if you train a neural network on the same problem, take that neural feature matrix and apply this neural feature matrix in the same way we applied the AGOP from the kernel method, it does a very similar thing. It dims out the background and extracts this band, arguably to a lesser extent, actually, than this AGOP from the kernel method. And we start to get some beautiful visualizations of like how does this feature extraction happen? Well, I've mentioned before, it's edge detection, and I mean this quite literally. So if you look at the eigenvectors, in the same way we were looking at, like the celebrity faces, with the eigenvectors being like different masks for like glasses and beards and lips or whatever. Here, the eigenvectors of the CNTK convar FM AGOP is literally these like different types of edge detectors. So you have the top 2 is a horizontal and vertical edge detector, and then you have some diagonal edge detectors, and then some of these are redundant as well. You get some horizontal and vertical edge detectors. And then if you increase patch size, you get a similar thing, but the edge detection gets a little bit more complicated. And the result is that if you look not just at the synthetic example, but on, again, SVHN, we see that a silhouette of these sketch digits emerges from applying these learned filters from both the CNN and convar FM, this recursive kernel method, over the whole image. And what's interesting is that these lessons apply as well to these state-of-the-art architectures. So if you download, again, VGG11 and you compute its AGOP and you apply it to these full resolution images, you get a complete edge sketch of these different images from the AGOP of a VGG11 network. And you can recreate the exact same features from this fixed kernel method, which wasn't even trained on ImageNet. It was actually trained on this SVHN dataset. And here on the right, this is a 3x3 patch, but as we increase the patch size, you lose a little bit of resolution, which makes perfect sense. So this is a 3x3, 3x3, and then 7x7 in the third column. And to really hammer home this edge detection point, so it's been observed that, in particular in the AlexNet paper, that neural networks, convolutional neural networks, are able to, or the filters in these convolutional neural networks have a striking similarity to a method from classical computer vision. So computer vision before there were neural networks, called Gabor filters, which are these little bands. So they're a matrix the size of a patch, they're represented by a matrix the size of some sort of patch, and they have a band in the middle that's oriented at a particular angle to extract an edge of a particular angle. So if your image is this circle, this white circle on a black background, each of these Gabor filters of a different orientation, when passed over your original image, highlights edges oriented at the angle perpendicular to the orientation of the filter. So here you have a vertically oriented filter. The result is that when you pass this over your image, you get, or I guess it's parallel. So you extract a vertically oriented edges, or here in the first filter in this third row, you have a horizontally oriented Gabor filter that extracts out the horizontally oriented edges. And somewhere in between, you have this angled one, and you extract out these angled edges. Okay, so this was taken from like the Gabor filter Wikipedia page or something. And if you take the eigenvectors of your AGOP RFM, if you're a kernel machine AGOP, and you apply these eigenvectors using the visualization we introduced earlier to this guitar image from ImageNet, we see the same exact thing happening. So these are horizontal edge detectors of different sizes. These were completely unmodified eigenvectors from this AGOP. This 3x3 horizontally oriented edge detector or filter, when applied over this guitar image, extracts this horizontally oriented edge at the top of the guitar in this line here. Same with this one, which is a little bit bigger patch size, and this one as well. You can also extract vertically oriented edges by taking these vertically oriented edge detectors, applying it over the images. So for example, this is a vertically oriented edge versus these horizontally oriented edges. Same thing here with a smaller patch size. And you can even get diagonally oriented edges. So now the diagonals are highlighted, and the horizontal edges and vertical edges explicitly are not highlighted. And to some extent, you see that here as well. So this method, am I doing time? Good. So this method, it explicitly modifies the input images. So this method I've introduced here. So it modifies the input images directly, but it doesn't, which is mimicking how the first layer of convolutional neural networks is doing feature learning. But you may say, well, there's probably some sort of feature learning that happens in later layers as well. And the answer is yes, that's definitely the case. So if you were to, and we have a method that actually mimics how deep feature learning happens in convolutional neural networks. And we call this the deep conv RFM. And what it does is it applies RFM on the first layer, and you get some sort of learned AGOP. And then you sample filters with covariance equal to this learned AGOP. And then you convolve your data and apply a nonlinearity with these sampled filters. And this gives you some new set of images on which you can again apply conv-RFM. So you apply conv-RFM, sample filters, generate new images, and then proceed to the next layer of feature learning, apply conv-RFM, so on and so forth. And we saw qualitatively that one layer of feature learning was enough on this kind of left synthetic problem. But with deep feature learning, you can really start to close the gap with how CNNs do on these local signal additivity problems. So on the left, this deep conv-RFM is already beating this green line. The purple line is the deep conv-RFM. It's already beating this CNN. And here, the bottom line is the fixed kernel with no feature learning. So it suffers a lot from increasing the amount of noise in the back. This x-axis is increasing the noise in the background of these toy problems. So if you have one layer of feature learning, you get a huge boost, but you still have a large gap with the neural network. And if you have another layer of feature learning, and this is actually, so this is 2 layers of feature learning now, then the gap between the gap is effectively closed with the neural network, at least in terms of scaling. These things scale essentially the same. So yeah, just more examples of you can recover features in the first layer, but you can also recover qualitatively similar features in deeper layers using deep conv-RFM on this SVHN dataset. And this SVHN, and this is like this. So this dataset is you put MNIST digits in the noisy background, and so you can also recover these kind of deep. We see in deeper layers, you're still getting edge detection just on these deeper representations in both. So in this right column, you have both the CNN, or sorry, in the right column, you have the CNN, and on the left, you have the AGOP from conv-RFM. And on real data sets, you get significant improvements on using this kind of approach. In particular, wherever the CNN is doing better than the kernel, you get some sort of significant improvement. And typically, deep conv-RFM using deep feature learning is better than just using one layer feature learning alone. So for future work, there's a lot of stuff that can be touched on with this. So I've described here how you can formulate feature learning in this light for fully connected networks and convolutional neural networks, but you can do the same thing or something very similar for transformers and RNNs. And we've actually done this, and the paper will come out very soon, hopefully in the next week or two. And it's a question we've also touched on a bit in this talk, but theoretically, how does this correlation emerge? How should we think about the similarity between the AGOP and the neural feature matrix as a consequence of training? And that's coming through current work on a theoretical understanding of the NFA. But I think this kind of lens lets us ask a lot of questions that were kind of previously inaccessible before. What is the role of pooling layers in feature learning? Maybe that can be viewed through some sort of interaction of the neural feature ansatz or the AGOP with pooling. And another, I think, important question is that I think in convolutional neural networks, especially, ADAM and SGD can do quite different things. And that is reflected actually by the features that are recovered by the AGOP for these different models trained with different optimizers. And so I think this is a nice case study in understanding these different optimizer choices. So all of these things I've just mentioned, I would classify under understanding feature learning and neural networks. But also a significant amount of this work was developing kernel methods that have introduced in them the feature learning mechanism we've identified in neural networks. And so I think that there is a decent amount of future work as well, just in continuing the direction we've set forth with these kernel methods. So all of the convolutional kernel method stuff I've told you guys about is just in fully connected type architectures. So CNN VEC, the kernel for CNN VEC, where you don't have any pooling layers. And for fully connected networks, there's obviously no pooling layers, or it's this is basically the simplest possible architecture you can come up with. So understanding, this is simply an engineering problem. Like, how can we implement an RFM type method with a more complicated architecture? Maybe as a start using pooling layers. So I think that's a good direction. And also just accelerating kernel computation. Like, that's actually been, for convolutional neural networks, convolutional kernels are quite computationally taxing. And so if you wanted to solve them exactly, and so I think it's important future direction, like using to utilize the techniques people have come up with already to simplify kernel computation and accelerate kernel computation for this kind of problem. Yeah, and so I think that's everything I wanted to talk about today. I think I finished just in time. So yeah, thank you all for listening. Happy to take questions.
Oh, yeah, let's thank Daniel. Is there any questions from any of the audience?
Okay, I guess one question I had, Daniel, was you sort of like showed that like the edge detectors, basically every layer of a convolutional network still behaves in edge detectors somehow, right? Like
Yeah.
like the color changed, maybe the resolution changed a little bit, but it sort of was doing the same thing, which feels very unintuitive to me. Like, is it just like a refinement? Like it's doing a better and better job in each layer? Because I expected, at least like traditional intuition said that CNNs, each layer did different things. Like the first layer found edges, the second layer like focused on like, I don't know, like eyes or something. The third layer was doing like more complicated like patterns. But this image sort of makes it seem like they're just doing the same thing over and over again, but maybe with slight modifications.
Yeah, I think they're not necessarily mutually exclusive perspectives. I think you can have feature learning be edge detection while having complicated features emerge, complicated sort of representations emerge from neural networks.
Oh, I see.
Bec
Visualization
yeah,
here, just the M matrix applied. It's not necessarily the output of the whole layer.
yes, exactly. Yeah. So there's learning that happens that's not feature learning, for example, right? Like you can, right. I think this is a big part of why it's difficult to study deep learning theory is that there's multiple things happening at once when you train neural networks. Obviously, but like you know, they're solving some sort of optimization where you have some predictor and it's trying to learn some sort of coefficients on that predictor in a way a kernel would, for example. But then there's also some sort of process where it's like learning features, right? And the feature learning part is not necessarily tied to the predictor learning part. And I think these things can both do interesting, non-trivial things. These processes can result in, on their own, both results in interesting things happening. And it's hard to know when you observe something about a neural network, is it due to some sort of predictor optimization or what we would think of as feature learning? And I think in what you're describing, I think you basically said it. Like, yes, there's some sort of transformation due to our notion of feature learning, but then there's also some transformation of the intermediate representations due to the left singular vectors and the non-linearity. So it's hard to separate. Yep. Yep. So for example, yeah, like clearly there's edge detection happening, but there's also, it's highlighting this like thing here, right? Like it's not all sort of in the middle part here or something. Yeah. So, yep.
Yeah, thanks for that.
Yeah, no problem.
Good question, I think, unless someone else has a question.
I have.
Okay, all right, yeah, go ahead.
So this is about the supervised learning setup, right? Do you have any perspectives on unsupervised feature learning, for example, like using SL or contrastive learning?
Yeah. So I forget who told me this, but I kind of feel like it's true that there's basically like no such thing as unsupervised learning. Like everything is like, there is like some goal, like there's always like something you're trying to estimate, I guess, or like so for example with I'm not an expert on this, but like self-supervised learning, maybe self-supervised learning is a bad example. PCA, just take PCA, right? PCA, you find what are you doing? You're minimizing, you're finding directions that like minimize variance in your data, right? Actually, this is an AGOP. It's an AGOP where your target function is like a squared norm of the data point. And so the top k PCA directions are actually the top k eigenvectors of the AGOP where your function is f of x equals the norm of x squared. So yes, you could say PCA is unsupervised because we don't have any label, we're not given labels. But PCA is actually supervised in the sense that we create labels, which is the norm of x squared, and we say like, what are the most relevant directions for this label for the norm x squared? So to me, that I think this framework, I think unsupervised learning can definitely be viewed in this framework. Just what it means for a direction to be relevant is that it's relevant for the explicit or implicit task you've created for yourself. Does that make sense?
So, yeah, thank you.
Yep.
Okay, I'll ask the last question, I guess. Thanks a lot, Daniel, for the talk. Yeah, I guess there's two kind of things going on here, right? There's the AGOP, and I guess from what you're saying, the AGOP is a general phenomenon for all learning methods, like kernel methods, neural network methods, unsupervised learning, etc. And then you have this connection between AGOP and the actual weights that you learn in a neural network, right? So these are kind of two separate ideas that you're talking about. Am I understanding that correctly?
Yeah, so I would say like the AGOP is not okay. So I don't think it naturally appears everywhere. Like I definitely don't mean that. I mean that it's like it is, however, in the way it is universal, is that if you have some sort of predictor, provided it is differentiable, it gives you don't even need to use it for anything. It just tells you what is the AGOP specifically. It tells you like what is the average sensitivity or the covariance of the sensitivity of the predictor I've already learned. And what we've done with kernels is say, well, you can just estimate the sensitivity matrix, and then you can actually improve kernel methods by just plugging it back into the kernel as a distance, as an inner product. And then what we find for neural networks is that they're actually automatically doing this. When you optimize a neural network, it's automatically updating its weights to store this AGOP or aligning its weights with this AGOP. The direction of causality is not totally clear. It's like the AGOP's aligning it to the W is aligning the AGOP. But in any case, it's automatically transforming its data with the AGOP as it's passed in the neural network by some sort of bias, you maybe could call it, of like the optimization algorithm plus the neural network or something. Does that make sense? That was a long explanation, though.
Can I also ask something? When you calculate, which function do you use to calculate it?
So here, for example?
Yeah, what is F?
F here is a kernel method, so it's alpha.
No, can you calculate it for neural nets, for example?
Yeah. So, right. So let's take the first layer. So here, this is L equals 1, so it's W1 transpose W1. So actually this one, whatever, this one's one. Okay, so it's like W1 transpose W1. So then this we're saying is proportional to the gradient. Here, X1 is the input to the first layer. This is just X. So it's the gradient with respect to X. The input of F1 is just the whole network. It's F. So it's the gradient of the whole neural network with respect to the input data.
So to calculate the AGOP, you need to basically have trained the network and get the matrices. So
yeah, I mean, you don't even need to train it. You can just if you give me a neural network, I can just compute this thing. All you need is a neural network, trained or not trained, and a data set. And if you didn't train the network, then this correlation won't necessarily hold. But if you train the network, and if you train the network on a different data set, then it won't hold for the data set you're computing the AGOP on. But if you train the neural network on the data set that you've given me, then what we will claim is that this correlation will probably hold. Yeah, I guess that's the claim. Yeah.
Understand. WL is the weight matrix of the network, right? And then
exactly
the gradient of the same network.
Yes.
Right? So basically, like the gradient of the network with respect to the previous input will be like the matrix times the derivative of the activation function given the previous input, right? So,
yeah, exactly. So
and for free, right? Like when you have W transpose W, it comes from the derivation of the neural network. Is that correct?
I think so. I'm not like completely sure what you mean.
Just trying to say that is the reason that these are proportional, is it because the function you derivate is the neural network itself?
Yes. Yes. So
I'm
for
just
an intermediate layer, yeah, so for this WL has to come from has to be the WL from this FL.
Yeah.
That's it. Yes,
say
yeah.
have two different neural networks that perform pretty well in the, like, let's say MNIST, right? And then I go and I use as FL the function of the one network, and I calculate the AGOP, and then I compare the matrices of that AGOP with the matrix of the other matrix, the other network. Probably that relation won't hold, right?
So I think it depends. So I think for the input to the first layer, you're taking the gradient of your model with respect to the input to that layer, which is the actual data. So it hasn't been processed at all by a neural network. So actually, the AGOP of a neural network, I think, because this AGOP of the neural network is estimating a statistic of the target function and the data, which is the EGOP, it doesn't matter if it's good, if your estimate is good enough, it doesn't matter how you estimate it. So you can use a good neural network, you can use a good kernel method, and they'll have the same AGOP. Or you can use neural network 1 or neural network 2. You can use a ConvNet or fully connected network. If they're trained on the same problem, the AGOP should be similar for the first layer. For the second layer and beyond, now you've incorporated specific stuff about the specific model you're using, because now for the later layers, it's now an embedding that comes from the specific neural network you're using. So now these things will no longer align necessarily.
And to say that like this layer-wise calculation of the AGOP should be network specific. Like at the end, we know that different neural networks do the same things, but each layer might be like significantly different. The weight matrices. So it would be that, for different networks that perform well in the same task, they all satisfy this condition. Like, let's say that I knew the underlying F star of MNIST and I take the gradients. Could I claim that, WL transpose WL for any network will be the gradient? I guess I cannot. Right? Like I'm trying to say that FL needs to be the network you're looking at to make that proportional relation, right?
Yes, in general, that's true. Yeah. However, I think there is I guess what I was trying to say before is that there's an exception for the first layer, because the first layer is truly estimating something about that is independent of the estimator.
Okay, Daniel, last question, and I'm done with that. If you did
No problem.
Your network, is the correlation just the strongest for like a deep MLP, for example? Like, did you guys look at like deep linear networks?
I think we later looked at deep linear networks. I think it's fine. It's just as good. It might be better even. I think it's not an exception. Yeah, I don't know if there's anything remarkable. We have actually a proof for one hidden layer, a linear network for multiple steps. But yeah, nothing. Yeah, I mean, go on, sir.
No, nothing. I was just saying, like, it's not necessarily stronger for like neural networks.
For linear versus nonlinear, I think there's not really much different in terms of this correlation.
Okay.
Yeah.
Cool.
Yeah, let's thank Daniel again for his great talk.
Thank you. Thank you.
See you.
Okay, see you. Bye.